Good day, everyone. Today I'm going to discuss about line contraction. So this is the second part of the video about special relativity. So previously I discussed about relativity of simultaneity and relativity of time intervals, and also a bit of introduction on special theory of relativity. So as you have noticed, there was this uh, an explanation or an attempt to explain the transformation, which is what we call the Lorentz transformation, which is occurring on the coordinate systems of the celestial bodies. So one attempt to explain that is this length contraction. But during those times, the explanation of Lorentz contraction is that if an object moves, so for example, this one, so it moves to the right, then it contracts because due to the force. So uh, the problem with this one is they say that it is in atomic level and even in the subatomic level. So the atoms are being compressed. And as we all know, this shouldn't be since the radius of atom cannot be affected by the motion. And so due to this, it is hard to prove and hard to disprove during those time because of the limitations of the measuring devices. And we have this review on the Lorentz transformation. So Lorentz transformation occurs probably they thought during those time because of this luminiferous ether, and we have these values for the gamma and beta. So gamma is the what we call the Lorentz factor, and beta is just the ratio of the speed of the body to the speed of light. And the alternative explanation to the Lorentz transformation, the line contraction. So we have here at velocity 0, gamma is 1. So if this is 0, we have gamma equals 1. So that fits to the observed phenomena, and also this one. So as the object moves to the right, it is compressed. And for example, to have a concrete idea on the Lorentz transformation, consider a dog that can live in the outer space, which is moving. These things are moving in relativistic speed. So we have a relativistic dog, relativistic bus, relativistic Tyrannosaurus Rex, and this one is quite techy, relativistic spaceship, and for example, a star moving at velocity that is fairly near at the speed of light. So if it moves, we observe that it is contracted. Hence, we have the Lorentz transformation of the coordinates. So, another review is we know that from the Maxwell's equation in a vacuum, considering that the space is a vacuum, um, we have the speed of the electromagnetic wave propagation at c, which is 299,792,458 meters per second. And the relativity principle, for example, if we have a spaceship shooting lasers at the speed of light, so according to the Galilean transformation, it will exceed c, but the Maxwell equations forbid this, so we rewrote all of those stuff and we arrive at the expression for the relativity of time intervals. Now, what about the measurement on the space or length? Consider here we have a volunteer. His name is Pepe the Frog. For example, Pepe is standing still. Its body length is L naught. So we have here a mirror, and from the bottom or from the tip of Pepe, we shoot a light beam. So it propagated from here to here. Of course, this is very fast, but for the sake of visualization, we'll just move it from here to here to the mirror and it goes back. So the time interval should be the same from here to here since it is not moving, and it should be twice the length of Pepe. So the distance traveled from here to here is just the same, so we multiply it by 2, and it is the whole trip is delta t naught, a review from the kinematics. So it's just delta t naught is 2 L naught over c, or the distance over the speed of the propagation. Now, if Pepe runs at relativistic speed, what will happen? So let us examine this. First, of course, Pepe will have traveled this distance at some delta t sub 1. For example, after 5 seconds, of course, Pepe will cover this distance time multiplied by the speed of Pepe. Take note, this is a relativistic speed, so it is very fast. Pepe is running very fast. This distance from here to here, so Pepe started here, and after delta t1, his location is here, but Pepe is still running. But for the sake of analysis, we'll stop at delta t sub 1. So what would be the distance traveled by the laser then? It's just the speed of the laser, c, times, of course, the time. And we can equate this to, saying that this is the same distance. So this one, c delta t sub 1, is equal to the body length of Pepe plus the distance traveled by Pepe. And you just have to manipulate it algebraically to arrive at the expression delta t sub 1, which is equal to body length of Pepe over the difference on the speed of light and the relativistic speed of Pepe. Now, for the round trip of this laser, of course, the laser bounces back. Pepe still runs, so the tip of Pepe is now moved by this distance. We have to subtract it because the full distance is now reduced because Pepe is moving towards the source. We have distance minus the distance traveled by Pepe. He reduced the distance. That's what this equation means. And of course, the distance traveled by light. Now, we equate these two. We have C delta T sub 2 is equal to L minus U, relativistic speed of Pepe, delta T sub 2. So this is just a continuation. Pepe is just continually running, and we examine the relativity principle and, of course, the Maxwell's equations. Now, we have here, we just manipulate the equation algebraically, and we arrive at the equation delta t sub 2 is equal to L over C plus U. So if we add this two, that would represent the whole trip of the laser. We have here, we already calculated this two, and it's just simple addition. We arrive at 2L over C times 1 minus U squared over C squared. Take note of this value. This is quite familiar. Yes, this is just the Lorentz factor squared. Take note of that. And of course, from the relativity of time intervals, we know that delta t naught times the Lorentz factor is just equal to delta t. But from the line contraction, we know that delta t is equal to 2L over C times this is just gamma squared, and delta t naught equal to 2L naught over C. So we substitute these two values, this one here, this one there. And of course, the rest is just simple math. We cancel C, we cancel 2, and this will be cancelled, and we're left with gamma here. This is gamma squared, this is just gamma. And we have an expression for the line contraction. So all we needed was just the combination of relativity principle and Maxwell's equation to arrive at the explanation for the line contraction. So there's no need for us to think that if you move, you are being pressed by some invisible force and your length reduces. Because you think about it, if you are indeed being pushed back, then if you stop, then the flattening of your face um should be visible. Does not happen. So the logical conclusion here is that due to the nature of the electromagnetic waves, or if I say as a whole, it's just that the wave contraction is the result of Maxwell's equations and the relativity principle. And combine that, we have special theory of relativity. Now, let's proceed with an example. I think we also have to revisit Pepe. So Pepe here, he wants to include himself. Pepe stationary versus Pepe running. That would mean that he is contracted by factor of gamma. Now, we go back to our examples. Let's single out this Tyrannosaurus Rex. So approximately the Tyrannosaurus Rex was reduced to a length of half of its original size. So we have here L naught over L would be 2. And we have here, we're left with the Lorentz factor on the right hand side. Then we square both sides. After, I think you have to multiply by gamma. I think 1 over gamma for both sides. And then you square here. Then we're left with, sorry, this should be the square root already of u. So you have to move by 0.87 the speed of light in order for your length to be contracted by, I think, by 2. So that's how fast this Tyrannosaurus Rex is, almost the speed of light. So Tyrannosaurus Rex is standing still and you measure it by 4 meters and it runs and you observe that it is now 2 meters, then that means that that Tyrannosaurus Rex is running at the speed of 0.87, the speed of light. So you multiply 0.87 by 299,792,458 meters per second. That's very fast. That's a very fast Tyrannosaurus Rex. And I think that would be all. Thank you for listening and thank you.